Hello students, good evening. Welcome to Gate Wallah. My name is 𝐂𝐚𝐿, Computer Science faculty. So we are continuing our lecture series on theory of computation. So in your previous 5 lectures, we have completed different topics. Let us see what are the topics we have completed. So in our previous sessions, one is DFA construction, deterministic finite automata. Deterministic finite automata construction. Second one is DFA detection. And then third one is NFA. Epsilon NFA, ENFA or epsilon NFA. So we can write so epsilon NFA. These are the major topics we have completed till now. Once again students, welcome to lecture series on theory of computation. Last week we have completed some of the very important concepts related to theory of computation. In that, finite automata is our major topic that we have completed in previous sessions. Major topic in finite automata is deterministic finite automata, DFA construction. From this, in almost in every gate, 1 or 2 marks we'll get. From where we'll get questions means these are the topics: DFA constructions, DFA detection. That means given DFA or not. From the given DFA language detection, DFA detection includes DFA identification, DFA to language detection. Then NFA, that to epsilon NFA. So these are the topics we have completed in the previous session. Actually today our topic is regular expression. After finite automata, next important, like DFA, NFA, after these concepts, next important thing is regular expression. Regular expression is one of the major concept in regular part, finite automata and regular language part, especially in the first topic of theory of computation. From this also easily will get 2 marks in the gate paper. We have one question in last year paper also. And before going to start this topic, actual regular expression topic, actually I have to start this. Before this, one more important concept is there in finite automata, DFA, that is minimization of DFA. So first we will study minimization of DFA, then we go for this topic. That is our plan, our today's plan. First we will study how to minimize the states of the DFA. This is one of the beautiful concept, important concept, many times asked concept in gate papers. So after this topic we will move to our regular expressions. So let us move to the minimization of DFA. Students, those who are preparing for gate examination, for them this topic is very crucial because there are a lot of confusions here. So many students generally confuse while studying this topic. So we'll study today what are the concepts where generally students confuse, how to make those concepts very simple to solve gate questions. There are so many questions from this topic in gate papers. There are so many questions. Whenever question comes from this topic, most of the times 2 marks question. So how to solve those questions? Let us study that. Before going to solve questions, first let us try to understand what is this concept minimization exactly. Here I am giving 3 finite automata to you, mainly DFA. For the question is, for one regular language. What is the regular language? The language for which DFA exists. For one regular language, how many DFA possible? How many DFA possible to construct? That is the question. That means if one regular language is given, how many DFA we can construct? Generally some students think that for one regular language means the language for which DFA possible. For one regular language, only one DFA. That is not the right way. For one regular language, many number of DFA possible. For a given regular language, even though many DFA possible. So number of DFA possible is many. Then where is the difference? If these many are possible, what is the difference in this? The difference is states. So let us see one language, complete language, sigma star. For complete language, first one is DFA, all states transitions exist. Second one is also DFA, third one is also DFA. Like this, how many we can construct for complete language? So many. That's why for one given language, for one given regular language, we can construct many number of DFA. Now the question is, if you construct these many number of DFA, which is best one? So this is the concept where the minimization of DFA comes. If these many DFA available, which is our best one, which is our preferred one? The DFA which is having least number of states. So least number of states DFA is the required DFA for that language. Okay. Now the question is, why we want all these minimizations and all this? Can we construct directly minimal states DFA while construction itself? So whenever we are constructing DFA for the language, can we construct minimal DFA at a time? Means that is almost not possible. Sometimes we may construct, but we cannot generalize that. We cannot construct any algorithm directly to construct DFA, minimal DFA at a time. That is impossible. That's why what we have to do is, but see, whenever we are getting questions, see all previous gate papers, see the theory of computation questions, mainly DFA questions. Whenever any question is there from DFA, like number of states, they will ask like this: how many states are there in minimal DFA? Otherwise, how many minimal state DFA exist for this language? So the question is always about minimal states. The whole concept is all about minimal number of states. So there are two important things. Whenever we are designing DFA, two things are important for us. First one is construction of a valid DFA. Whenever we are constructing DFA for a language, construct a valid DFA. That is the first point. Second one is, just a valid DFA construction is not enough. The DFA should exist minimal number of states. So for this language, take this example. For this language, complete language, this is one DFA one student can construct. This is the valid DFA other student can construct. This is the valid DFA other student can construct. So if these many DFA exist, what is our required one? What is our best one? That is the first one. Minimal state DFA is the required DFA. So now the concept is, if assume some student is constructed this way, I told you already, there is no procedure to construct directly minimal state DFA. By practice, sometimes you may get, sometimes you may not get. So if anybody constructed like this, we have procedures or we have algorithm to turn this into like this. Any more states, more number of states DFA to convert into minimal state DFA, we have algorithm. If we have two state DFA, if I apply minimization algorithm on this, it will convert into one state for this language. for 3-state DFA for the same language, complete language, if I apply minimization algorithm, it will turn this into the first one. That's why to construct a minimal state DFA directly, we don't have algorithms. But if a DFA exists, to turn that into minimal states, we have algorithms. So in today's session, we are going to see those algorithms. This concept is very beautiful. So many number of states will be given. We'll try to reduce them with less number of states. That is minimization. So how we'll do that minimization? That is what our today's topic. Right. But remember one point, one important note. Hi. Welcome to, some students are joining. Good evening again. Welcome to Theory of Computation lecture series. Today our session is on minimization of DFA. Right. Right. So this is about minimization. We are reducing the number of states of the DFA. Possible number of states. How many least states possible for that language? We are turning the DFA into like that resultant DFA. So some people are saying happy Holi. Happy Holi to all of you. My belated wishes. Right. One important thing before applying minimization is, if you want to apply minimization, these minimization algorithms, we have a minimization algorithm here. There are mainly two things: state equivalence algorithm, table filling algorithms. If you apply this algorithm, then number of states of the DFA will be reduced. YouTube पर TOC का पूरा सिलेबस होगा. YouTube में कुछ टॉपिक्स होगा अभी तक. That means this is the English channel. Here I am teaching some topics. Some of the topics still now I think in the next series. This is first lecture series, right? Mostly I'll cover remaining topics in the next series. But that may be in English channel or Hindi channel. I don't have that information till now, but it will be covered. Right. Now the important thing is, this minimization, if you want to apply this minimization, your automata should be DFA. So algorithms we can apply only for deterministic finite automata, only for DFA. If your automata is deterministic finite automata, then only we can apply minimization algorithms. Yes, I will provide required information. Some people are asking about Telegram, WhatsApp. Mostly by tomorrow session I will able to provide. I will provide you required information. Okay. Right. Let us move to this topic. If you want to apply these algorithms, given automata should be deterministic finite automata. Deterministic finite automata. If it is NFA, the problem, what is the meaning of this? If your automata is non-deterministic finite automata, NFA, or your automata is epsilon NFA, these algorithms are not applicable. We can apply these algorithms only for deterministic finite automata, DFA. So let us come to see these algorithms through some example. Hello students, welcome to Theory of Computation lecture. Good evening to all of you once again. Today is a beautiful concept, reducing the states of the DFA. So let us enjoy this session. So this is the DFA. This is one of the DFA. We need to eliminate some states from this. First of all, I told you this minimization algorithms, this concept, whatever we are studying now, applicable only for DFA. If your automata is DFA, then only it is suitable. If it is NFA or epsilon NFA, we cannot apply this. So first let us check this, whether it is DFA or not. Any one of you, can you confirm me whether it is DFA or not? Is it given automata is deterministic finite automata or not? What is DFA? From every state on every input symbol, exactly one transition exists. DFA means from every state on every input symbol, one transition exists. So this is, some people are saying this is not a DFA. Where is the violation? Can you tell me on which state it is violating? Our DFA definition. Some students are saying more than one final state. More than one final state is not at all a problem for DFA. Watch our DFA definition class recording once. Some people are asking to provide all information, all lecture series in YouTube. I will try. So in this series, I am planning for only some part of the syllabus. So keep on watch my videos, coming videos. Mostly by end of May or June, it can be available. I'll try to take live classes of all topics. Right. कोई हिंदी वाला है तो अगर आप हिंदी चैनल में, इंग्लिश चैनल में देख लीजिए. सो 3-4 मंथ्स तक मोस्टली टॉपिक्स यूट्यूब में अवेलेबल होने का ट्राई करेंगे. So GATE 2025, your one class is equal to 10 classes. Thank you very much. So whenever any depth concepts are going on, if you are feeling any confusions, this is a recording one. So you can take the recordings available in our YouTube channel. So you can watch those recording. If you are still facing any difficulty in the next class, you can ask me in the chat box. Right. Let us see. This explanation of this takes some time, almost 15 to 20 minutes time it requires. Slowly try to understand. Let me try to clear all the concepts properly. If you are having any confusion, then you can ask me in the chat box. I can clear for you. Right. So here some people are telling this is not a DFA, and some people are saying directions are wrong. So my answer for this is, to perform minimization, first thing is detection. Given thing is DFA or not. So to say this is DFA or not, what is our definition? From every final state is not a problem. One initial state, any number of final states, even if final states not exist also not a problem. All these things we discussed in our DFA definition class. So if final state is there or not there, not a problem. Any number of final states there also not a problem. Right. What is DFA? Every state, every symbol transition exists or not. From this, on 0 transition exists, on 1 transition exists. From this, 0 transition, 1 transition. From this, 0 transition, 1 transition. From this, 0 transition, 1 transition. Every state clearly there. All the transitions of all these states clearly exist. For every state, every symbol transition exists. This is clearly DFA. Still, anybody having doubt in this DFA detection? We are not worried about edges directions. This type of example we already studied in our definition class. We are not bothered about transition directions. We are not bothered about states connected or not. We are not bothered about final state exist or not. All these things studied, right? Now the thing is how to do minimization. Here total 6 number of states are given. This is a valid DFA for one language. Number of states given are 6 number of states. These many states not required actually. We can eliminate so many states. We can reduce so many states. What are those? After eliminating all these unnecessary states, how many remaining states present in our required DFA, resultant DFA? That is what our aim is. This minimization is actually done in 2 steps. So let us see. We'll eliminate in the first step some kind of states, in the second step some kind of states. So total elimination process we are doing in 2 steps. Let us see what is it. The first point here is eliminate all inaccessible states. First thing here is eliminate all inaccessible states. What is the meaning of inaccessible state here? This is our first point. All these are comes under second point. This is our first point. Eliminate all inaccessible states. Now what is inaccessible? Any state which is not reachable from initial is inaccessible. If any state is not reachable from initial state, that is inaccessible. First, remove those type of states. That is our first step. That is not the final answer. That is the first step. So let us try to understand this. This is very easy. If any state is not reachable from initial, if you are traveling from initial state, anything is not accessible, remove that. That is the first step. Easy one. Can you tell me what are the inaccessible states in this? According to the previous definition, what are the inaccessible states? The state inaccessible means states which are not reachable from initial. From the initial, what are not reachable? Identify those. Tell me what type of states are not accessible from the initial. Any answers from anyone? Right. Let me try to give this. What are the inaccessible states here? Some people are saying Q2, Q3. Okay. Any other answers? Two and 4. Okay. Good. Start from travel. So I think for some people it is a hobby. Traveling from one place to different places. Like this, travel, enjoy our traveling here. Start from initial state. Let us travel. Start from Q0. We can travel to Q1 by this path. Q1 is reachable. Means what? Q1 is reachable, accessible. From here we can travel to Q3. That means from here we are reaching means from Q0 also we are reaching. This is also accessible. Reachable, no? Reachable. From here this is accessible. We are reaching here. So from Q0, Q1 is reachable, Q3 is reachable, Q4. The paths are like this. Let me show the path as well. This is a graph, like your graph theory. Right. Now the question is, directions are clearly mentioned. The direction of this one is this way, direction of this one is this way. From Q1, can we travel to Q2? One way, traffic police exist here. You will get fine. You will impose some fine. So Q1 From Q1 we cannot reach to Q2. From Q1 we cannot reach to Q4. From here we cannot reach to Q4. Q2 is not accessible state from initial, inaccessible state. Here Q2 is inaccessible state because from initial state Q2 is not reachable. From initial Q4 also not reachable because through this path we are not reaching, we are unable to reach. Through this path also we are unable to reach. So here Q2, Q4 states are inaccessible states. Is it clear for everyone? So out of all these 6 states, 2 states are gone. Q2 and Q4 states are inaccessible states. What we have to do? Remove them from our DFA. Remove these states and remove their transitions as well. So this total part, whatever is there, this total part will remove from the DFA. This is our first step. So while doing minimization, the first step is remove all inaccessible states, detect inaccessible states. Wherever inaccessible states exist, remove them. What are the inaccessible states? Any states not reachable from the initial. Here we identified Q2 and Q4 are inaccessible, remove those. If you remove, the resultant automata looks like this. Q2 and Q4 are removed, then Q0, Q1, Q3, Q5. So this is the automata. Now on this automata, we have to apply our second step. Apply algorithm steps. We have an algorithm here. Actually, there exist 2 algorithms here, state equivalence algorithm, table filling algorithm. Any one algorithm is sufficient. We are going to solve gate questions. So to solve gate questions, they don't ask any specific method. Solve by this method, solve by this method. So the easiest one I feel here is state equivalence one. So we are going by state equivalence algorithm. See, in my classes, I don't teach you generally algorithm exact steps. I'll teach you how to solve the questions in the easiest way. Inside algorithm procedure is anyhow implemented. Try to understand the procedure. Right. So what is the next one here? After eliminating, apply second step. Second step is state equivalence algorithm steps. In that, first point is, let me change these colors. Separate all finals and non-finals. Yes, only logic. I'll explain you only logic. I don't write the moment I say algorithm. Some students expecting code of that. So it is not any C language. I am not going to run the code. I am not going to execute the code. That is not required in this subject. Algorithm means the procedure, step-by-step procedure of that one. So here the first step to apply this algorithm is all non-finals separately arrange in one group, all finals separately arrange in one group. That is the first one. So all non-finals here, Q0, Q1 arrange in one group, all finals Q3, Q5 arrange in one group. Some students, what mistake generally there is, most of the times many students do this mistake. After eliminating inaccessible state, they'll conclude this as the final answer. So they'll say, sir, 4 states is the final answer. That is not the way. Elimination of inaccessible states is one step only. With that, we don't get minimal states, exact minimal states. So after eliminating inaccessible state, you have to run these algorithm steps. You have to apply these algorithm steps. After applying the algorithm steps only, we'll get the correct answers. Because still this automata also can be merged further, can be minimized further. That also we have to see. Right. So first step is write all non-finals as one group, all the finals as one group. Then next one is, listen carefully. In the next step, we have to check these two are again grouped together or not. Q0, Q1 can be grouped together or separated. That one we have to see. That means that is called as equivalence. So Q0, Q1 are equivalence. We'll use this terminology actually in algorithm, so we can use that, not a problem. Q0, Q1 are equivalent or not. To check that, we have to see the result of this. For that, I'm taking transition table here, because if you see the transitions in table, it is easy. You can observe from here also. This is more easy. Without confusion, you can see directly. So if you want to check Q0 state, Q0, Q1 equal or not, let us check the transitions of Q0, Q1 on 0 as well as on 1. To check these two states, Q0, Q1 equivalent or not, we have to see their transitions. First, observe their transitions on 0. Q0 on 0, Q1 on 0. What is the result here? Q0, Q1. Here we have to take a conclusion. Q0, Q1 states on 0 transition, if the result falls under the same group, they are equal. Falls under the different group, they are not equal. This is the conclusions we are making here. To say Q0, Q1 states equal, their 0 transition should fall under same group. Their 1 transition should fall under same group. Let me repeat this once again. To say Q0, Q1 are equal, Q0, Q1 0 transition fall under same group. 1 transition should fall under same group. If that is not the situation, they are not equal. So what happens here? Q0, Q1 on 0, result Q0, Q1 falls under same group. Falls under same group. On 1, Q3, Q3 falls under same group. So 0 transition, it should not fall under different groups. If it is falling under different group, we will say it's not equal. If they are falling under same group, they are equal. So what is happening here? On 0, falling under same group. On 1, result falling under same group. So with this, we can say they are equal. Similarly, now we have to check whether these two are equal or not. Q3, Q5. If they are equal, we will group together. If not equal, we will separate them. So to check, the process is same. Now onwards, the procedure is same. So Q3, Q5. To check Q3, Q5 equal or not, take Q3, Q5 0 transition. Q3, Q5 0. Q5. One state can fall under only one group. Similarly, Q3, Q5 on 1. Q5 falling under same group. So to say Q3, Q5 are equal or not, it's 0 result falling under same group, 1 result falling under same group. So we can say Q3, Q5 are equal. So that's all about this algorithm. Take any two states, they are equal or not. What is the equality checking? Take their 0 transition, check falling under same group or not. 1 transition falling under same group or not. If falling under same group, they are equal. They have to write together. Falling under different groups, they are separated. That's all. Simple algorithm. So here in this case, Q0, Q1, 0 transition, same group, 1 transition, same group. They are equal. Similarly, Q3, Q5, 0 transition equal, 1 transition equal. We have to continue this further until previous result, present result are same. Whenever previous and present result are same, you stop the process. Here what happens? The present one Q0, Q1, previous one same. Whenever present and previous are same, you can stop the process. And then we can conclude that every one group make it as one state. So the final step of this one is we can rewrite, we can reconstruct a DFA by making every one group as one state. So here total how many number of states exist? Q0, Q1 together we can make it as one state. Q3, Q5 together we can make it as one state. So if you want to construct a new DFA, Q0, Q1 together one state, Q3, Q5 together one state. This is our initial state. So total how many states? This is a question asked one time in GATE. 6 number of states are given. Total 6 states are given. He is asking us to reduce the number of states. Exact minimal number of states. The exact minimal number of states for this is 2 states. That means whatever the language exists, the transitions also we can draw on 0 same, on 1 going here, on 0, on 1. This is the exact minimal DFA. This is about minimization. So reducing any DFA of these many states, 6 number of states, into just here 2 states. For some example it may be 3, some example it may be 4. So this is about the way of reducing the number of states, that is called as minimization algorithm. So how we are doing? Just let me repeat this once again, roughly, not completely. So first step is eliminate inaccessible states. That is the easiest one. Eliminate inaccessible state. And second one is grouping states together. All non-finals in one group, all finals in one group. Then check every 2 states are equal or not. Every 2 states are equal or not. If you apply this way, so after applying our first step, 2 states eliminated. After applying second step, 2 states eliminated. So that's why total number of states for the final answer is 2 states in the minimal DFA. And here this step is the important one. The second step here is applying algorithm steps is the important one, and easy one also. Right. Any confusions in this? Any confusions? Finals, non-finals, all non-finals write together, all finals group together. This is the one thing. Then take every 2 states, check their transition, falling under same group or not, verify. Falling under same group, they are equal. If not falling under same group, they are not equal. Right. So this is the way we can reduce states of the DFA. So see how beautiful it is. Total 6 number of states, this much bigger DFA, just to minimize it to like this. This is actual answer. This is actual answer. This much bigger one is not required. This much is sufficient to accept same language. Language is same. To accept same language, this is sufficient. But generally in the questions, this is also valid one. These type of things will get in questions. Our aim is transferring this type of DFA into like this small states DFA is what actually we have to do here. So these type of questions many times asked in our previous papers. So we have to practice. Previous questions we can practice some here. Remaining you can practice by your own. Okay. Let us try to solve one more of this kind. That is also asked one time in GATE paper. Consider the following finite state automata and construct minimal DFA. Construct minimal DFA. This is a 2-mark question asked one time. So we'll apply 2-step algorithm. In our algorithm actually we have 2 steps. First one is eliminate inaccessible state. Eliminate inaccessible states. What are the inaccessible states? The states which are not reachable from initial start from Q0. We can access Q1. We can access Q2, Q3. So Q3 is the state that is eliminated in the first step. Q3 eliminated. Apply second step of the algorithm. You can construct the remaining, after eliminating Q3, the resultant DFA you can construct here. Let me design that one. So after eliminating Q3, resultant automata looks in this way. So let me construct this. First take the transition table, so it will be useful for us. Without transition table you can do. Some students can confuse with this. That's why I'm explaining. If you are familiar with this concept, then you can even perform the same thing without transition table. Q0 on A, Q1 on B, Q0. This is on A, Q2, Q1, Q1, Q2. This is a transition table. So this table is just to check our transitions falling under same group or different group. Whenever we are applying the second step of the algorithm, we have to verify transitions falling under same group or not. For that, if your table exists, it is easy for us. It takes less time. Construction of table also just a copy from here. This is not a difficult one. Right. So what is in the second step? I'm applying algorithm steps. In that, what we have to do? Separate all non-finals and all finals in different groups. While applying algorithm step, the first thing is all non-finals write in one group, all finals write in one group. Right. Then whenever in any group more than 2 states exist, 2 or more states exist, then every 2 states equivalent or not we have to check. Here in this group we have only 1 state, no need to verify. For this group, Q1, Q2, are they equal or not? For that we have to see the result. To verify Q1, Q2 equal or not, Q1, Q2 A result we have to observe. Q1, Q2 A result falling under same group or not. Q1, Q2 A result falling under same group, they are equal. Q1, Q2 B result falling under same group, they are equal. Whenever they are falling under different group, then only not equal. So what is happening here? Q1, Q2 A result, Q1, Q2. So Q1, Q2 belongs to one group, they are equal. Q1, Q2 B result, Q1, Q2, that is also falling under same group, they are equal. So our the next step is Q1, Q2 again equal. Continue this procedure until present and previous steps are equal. Now what happens? See, present and previous are equal here. Stop the process. Stop the process. Every group consider as one state. So now what happens? This is one state, this is one state. So total how many states here? Total number of states is just, you can answer from here as well. No need to construct a new one. 2 states. Yes. Falling into same group or not, that is the main concept. Take any 2 states, whether falling into same group or not. Take any 2 states, falling into same group or not. So if this concept is familiar, we can solve questions very easily. So here also the given machine is 4 state machine, but 4 state not required here, just 2 states sufficient. The two states can be constructed this way. B, A, this to final, A comma B. That's all. This is a minimal DF, 2 state machine. This procedure also will not take more than 2 or 3 minutes time. When in a gate paper, we can solve this easily. Eliminate inaccessible states and check this grouping. If we are able to perform this grouping properly, we'll get the number of states. So this is 2-mark question in gate paper. So 4 states given. For this, minimal DF requires 2 states. Is it clear? Is concept clear? I will give you one question as homework for you. You can try by your own. Which answer you are getting for this? What is the answer you are getting for this? You can tell me in the next session. This is the question. All these are previous gate questions. All these are previously asked questions in gate papers. This is the 7 states DFA. He is asking us to reduce so how many states you are getting in the minimal one? So just you can pause after, whenever you are watching the video, just pause this video and you can note down this and how many states you are getting for this DFA in a minimal DFA. That is what required for us. Okay. So with this, we can end this DFA concept. How do you feel DFA, deterministic finite automata? So the major important concepts in DFA are DFA construction, DFA minimization, DFA to language detection. Right. So with this, I can move to our next one, next concept for today's session. Regular expressions. After DFA, after this in finite automata, DFA, NFA, epsilon NFA, after this, especially in regular part in the sense finite automata and regular language concept in that part. So regular expression is one of the important topic. So regular expression is also related to regular language and finite automata, DFA. So our next topic will be this one. Right. So I'll just give introduction in today's session about this. The depth knowledge of this solving questions we'll see in the next session. Let us try to understand what is regular expression in today's session. Regular expression is nothing but mathematical representation of a regular language. So if you want to see here, let me stand this side. Mathematical representation of regular language is known as regular expression. Regular language and regular expression both are same. There is no much difference. Way of representation is only the difference. If you want to show any language, especially the language accepted by DFA, if any language accepted by DFA known as regular language. Regular languages are nothing but language suitable for finite automata. Language suitable for finite automata known as regular languages. Those regular languages can be represented in two ways. One is language representation, one is expression representation. That expression representation is called as regular expression. Let me give one small example. We have taken a language a power n, b power m. N comma m greater than or equal to 1. Now if I ask the question whether this language is regular language or not, is this language regular or not, means for this language DFA possible or not, our answer is yes. because we can construct a DFA or finite automata for this language. We can construct clearly DFA or finite automata because there is no dependency here. We don't have any dependency. Any number of A's, any number of B's can be possible. So the language of DFA, for any language DFA exists, you can represent that language by this way. This is language representation, and same thing we can represent like this also. This is called as regular expression. So language is set of strings. Whatever the language accepted by DFA, those languages can be represented by set format, that is one way, expression format, that is regular expression. So this is called as here regular expression. Regular expression. What is the main advantage of regular expression is, say this language, to represent this language this much bigger way, we have to show in this way, space. So the general definition of regular expression is simplest way of representing regular language. Simplest way of representing is regular language, known as regular expression. Right. If that is the case, let me ask one question. Can someone tell me what is the regular expression for this language? What is the regular expression for this language? Any answers? What is the regular expression for this language? A star, B star. N value greater than or equal to 1 onwards. Whenever we are studying any concept, initial thing is we have to relate this with, in the regular, we have to relate this with finite automata. Forget about regular concept. What is the regular expression? Can you tell me how many states are there in DFA if we construct DFA for this? How many states are there in minimal DFA if we construct DFA for this? Minimal DFA. How many states exist in minimal DFA if we construct DFA for this? Any answers? DFA states. If I construct DFA for this, how many states in that DFA? The answer is clearly DFA not exist. DFA not exist. Comparison, dependency, DFA not exist. Then what is the regular expression for this? Now tell me what is the regular expression for this? This is the answer, right? Is it DFA exist? a power n, b power n greater than or equal to 1. You apply Arden's method, whatever the method you want. Is it DFA exist? If DFA not exist, is it regular? So this language is non-regular. A power n, b power n, n greater than or equal to 1. Clearly non-regular language. Regular expression concept is only suitable for regular. So regular expression means DFA exists, it becomes regular, then regular expression exists. All these three are equal. DFA, see, this is the equality. Whenever you say regular, definitely DFA should exist for that. DFA exists, then regular expression exists. Clear? If you want to say regular, DFA exists. If you want to say regular expression also exists. All these three equal. If any one thing exists, all are exist. So there is a equivalence between these three. So once a language is not regular, DFA not exist, we cannot construct regular expression for this. So the answer for this is regular expression not exist. Clear? A star B star is not the regular expression equal to this. This is wrong. This is not a regular expression. So reasons and all this clearly we'll see in tomorrow's session. So some people are asking Arden's theorem and all this. Those things we'll study in the coming thing. So the final conclusion for this is, whenever you want to construct a regular expression, first verify DFA possible or not. Regular expression also continuation of our previous DFA finite automata topic. It is not a new one. Okay. Okay, students. Thank you. That's all about today's session. Just now today we have seen the introduction of regular expression. Tomorrow actually what is regular expression, how to construct regular expressions, those things we are going to study. Okay. Thank you all. Bye bye. See you in our next session.